Hello everyone, welcome to NS Institute, an institute to publish Novel of Success. This is the first class of complexometry. In this class, we will try to learn the complexometric titrations and different kind of reactions, their examples and some kind of applications of it. First of all, we have to know the principle of these complexometric titrations or reactions. So basically see that these kind of titrations is generally or is mostly used for titrating different kind of cations. And the usefulness of this principle is based on the fact that as the titrants react almost completely with the cations, because here the cations are system to be titrated. So basically in the titration there will be two things. One would be the system to be titrated and another would be the titrant. Titrant means that through which we are going to titrate, and other things would be system to be titrated. So basically here the titrants react almost completely with the cations. Cations are those which cations are those system which will be titrated, and thus it provides a sharper endpoint, and also they react with the metal ions in a single step process. No multiple step is involved in these kind of complexometric titration. And the formation of these complexes serves the basis of accurate and convenient titrations of the metal ions. Now, through these titration, actually, we can get the data about how much of the titrant has been consumed, and by that data, we can back calculate the concentration of the metal ions were involved in the system to be titrated. And here actually the multidentate ligands are generally preferred for complexometric titrations because their reactions with cations are more complete and they react in a single step, forming usually 1:1 complex. So overall as a summary we can say that it is mostly used for titrating different kind of cations, and basically here the titrants will react with different kind of cations and that thus provide a sharper endpoints, and from that data we can get how much titrant will be consumed, and by which we can calculate the concentration of the metal ions involved in that kind of titration. And basically here different kind of multidentate ligands are preferred because of that complexometric titrations with these cations are more complete. Why? Because they react in a single step, forming usually 1:1 complex. 1:1 complex means that one metal ion will make a complex with one ligand. That's why it is named as 1:1 complex. See that when we are learning about these complexometric titrations, then we cannot ignore the structure of EDTA, because see this EDTA is one of the mostly used chelating ligand in these kind of complexometric titrations. So here I have shown you the overall structure of this EDTA, so you can take a note of it. So this EDTA is basically ethylene diamine tetraacetic acid, and this structure is already shown in the slide. And it is basically a hexadentate ligand, and it can form a very strong or very stable 1:1 complexes with most of the metal ions. Now, when such complex formation reactions will be rapid or reversible, will be rapid and reversible, the metal ions may be quantitatively estimated by titrating known volume of their solutions with standard solution of EDTA, which is named as direct titration. Or you can titrate a known volume of standard solution of EDTA with the solution of these metal ions. Then in that case it would be named as back titration. Here I have shown you basically two structures of this EDTA. The first structure is completely neutral. Why? Because all the carboxylic acid groups and the amine groups are having no positive or negative charges, whereas in the second structure the among the 4 carboxylic acid groups, 2 are forming the carboxylate ion and the amine groups are now protonated. So the second structure may be called as a Zuiter ion structure. Now the IR study shows that the second structure is the preferred structure, or it will be a stable structure. Now the EDTA is mainly assigned or generally assigned by the formula H4Y, whichever or in that manner in which manner I have shown you in the slide, or sometimes it also may be assigned by H4EDTA. So this is basically I have shown you at the right part of the slide. So either it can be assigned by the formula H4Y, whereas in some kind of books it is assigned by the formula H4EDTA. So here I have tried to show you how a typical metal EDTA complex looks like, because see that I have already mentioned that EDTA is behaving as a hexadentate ligand and it will try to form a complex that is 1:1 complex, which will be highly stable with most of the metal ions. See that the metal ions are the metal ions are forming bonds with 2 nitrogen atoms and 4 carboxylic oxygen atoms of that EDTA ligand. So thus the EDTA ligand is behaving as an hexadentate ligand. So it will be a overall chelate complex, that the metal ligand chelate complex. And as we know that because of that chelating nature, it will be highly stable in nature. Now we have already seen the structure of these EDTA. But see that in that kind of structure there are 4 acidic hydrogens, but in aqueous solution the complex forming ion is H2Y2-. Why? Just look at the statement whichever I have written just below of it. This is the acidic nature of EDTA. Now it has already 4 acidic hydrogen because the hydrogens are attached with that carboxylate group, but their pK values are 2.0, 2.7, 6.2 and 10.3. Now if you do consider the neutral pH value as 7 of water, then we must know that the pK values which are representing as 2.0 and 2.7, those would be, or those would show as the acidic hydrogen, whereas the 10.3 and 6.2 pK values which are responsible for those hydrogen, that may not show the acidic character in aqueous solution or in neutral aqueous solution. So therefore the pK values 2.0 and 2.7 which are responsible for those 2 hydrogens, those will be definitely acidic in nature in aqueous medium. So therefore it would be means it would behave as a dicarboxylic acid. Now there are also 2 amine groups. We know that amine behaves as base in nature. Amine is actually basic in nature, but see that the first of which it ionizes at 6.3 and second one ionizes at 11.3. Now again if we do consider the neutral pH as 7 of water, now around 7, it is the 6.3 and 7 is almost the same value, and the 11.3 is far is far more than this neutral pH value. So therefore at neutral pH or at aqueous medium, these amine groups will not show its basic property, or it will not attract the hydrogen ion. Why? Because in the neutral medium or in the aqueous solution the pH would be some kind nearly 7, and at that pH it would not show its basic character, because the pH values at which the amine will be ionized is around 6.3 and 11.3. Okay, so EDTA is actually very much widely used as a titrant because it combines with the metal ions in a 1:1 ratio. We have already covered that how EDTA is going to form 1:1 complex with different kind of metal ions. Here I have tried to show you different kind of metal ions with +2, +3, +4, or the charges may be varied, but each and every case whenever the metal ions are going to react with H2Y2 minus, they may form similar type of complex with the release of H plus ions. Here I have tried to shown the EDTA as H2Y2 minus. Why? Because we have already known till now that EDTA is stable as H2Y2 minus in aqueous solution, because in aqueous solution it will behave as a dicarboxylic acid. And in the second point I wanted to mention that EDTA is an important reagent not only because it forms chelate with all cations, but also because most of these chelates are sufficiently stable to form the basis for a trichromatic method. See that these metal chelates, see that EDTA is forming different kind of metal EDTA complexes, and that will be the chelate complexes. And you have to keep in mind that in these metal chelate complexes, the rings there these metals are and EDTA are forming will be 5-membered, and we know that the 5-membered rings are very much stable when we are considering the steric repulsion or the Beer strain. We know that, right? So thus these metal EDTA complexes will be highly stable, and therefore it would be a very important criteria for this trichromatic method. Here I have tried to show you one reaction that the metal ions is reacting with HIN2 minus, that is the acidic form of the indicator, to be converted into metal indicator complex with the release of these H plus ions. Now this metal indicator complex can react with these EDTA to be converted into metal EDTA complex with the release of these indicator and release of H plus ions. Now these can be possible when metal EDTA complex will be highly stable, and that's why EDTA is playing an important role, because the EDTA is forming very high stable complex with these metal ions, and that's why these metal EDTA complexes will gain that kind of stability that the second reaction will be more preferred, because the metal EDTA complexes will be more stable than the metal indicator complex. So therefore in the last step the reaction will be highly feasible that metal indicator will be converted into metal EDTA complex by the application of EDTA. So therefore it is very much important why we are considering EDTA as the most widely used chelating agent, because they are forming a very much stable metal EDTA chelate complex, which is the basis for a trichromatic method. Now, we have already mentioned that EDTA is behaving as one of the most widely used chelating agent or complexing agent in these kind of complexometric titration. So the next question should be in our mind that why EDTA is selected as the most suitable complexing agent? Why not other agents? See, because the complex formed between these metal ions and the ligand, that is the EDTA ligand, should be highly stable, right? That should be our primary that should be our primary consideration, that the metal ligand complex should be highly stable. So how the metal EDTA complex will be highly stable? So the stability will be dependent upon 3 factors. First one will be the chelating effect, second one will be the steric hindrance or the steric effect, and third one will be the bond strength. I will try to explain as much as possible with these kind of effects, or I will try to explain all these kind of effects as much as possible so that your doubts will be cleared. See that the greater number of donor atoms of a ligand will have, the greater is the number of ring it can form, and hence greater will be the stability of the complex. That is mainly named as the chelate effect, right? So basically EDTA is one kind of hexadentate ligand, so therefore it can form multiple ring, right? Because it is a hexadentate ligand, so thus it can form multiple rings, then the complex will be highly stable. Moreover, the rings are 5-membered. If you just consider the structure whichever I have shown you in last few slides, that the structure will be highly stable. Why? Because the rings are 5-membered, and we know from our basic knowledge that the 5 members ring are basically free from bear strain. Now the second thing was that the static hindrance. Now the static hindrance is the inhibition of complex formation due to the presence of a bulky group either directly attached to or to the vicinity of the donor atom. But in EDTA, no such bulky group is there, so there is no question of this kind of static hindrance. It would be statically free, right? And the electronegativities of these oxygen and nitrogen are such that they can form stable bonds because they are highly electronegative element. Besides, most of the metal EDTA complexes are colorless, which makes the detection of the endpoint easier because it will form a colored to colorless complex, right? So because of these kind of things, the endpoint would be sharp and detection of the endpoint would be easier. And one step formation of a single stoichiometric complex rather than stepwise formation of several complex. I have already mentioned that it would be a 1:1 complex 1:1 complex forming reaction, that is a single step reaction, not a multiple step reaction. So that is very much effective when we are trying to determine or we are trying to consider the selection of these suitable complexing agent. And again, simple monodentate complexing agent like NH3 is never used as a sharp endpoint corresponding to a single stoichiometric complex is very difficult to achieve. This is because the stepwise formation constant are closed together and they are not very large. But in case of EDTA, it will always form 1:1 complex and they are formed only in one step, and that's why it is coming into the picture. It is gaining so much importance that we are considering it as the most suitable complexing agent in complexometric titration. Now we have already seen that in the structure of these EDTA, 2 hydrogens among 4 will be highly acidic in nature, and therefore EDTA will behave as a dicarboxylic acid in the aqueous solution. But it should be noted that even at lower pH even those 2 hydrogen atoms cannot behave as acidic in nature. Why? Because if we just make the pH lower, or if we lower the pH, then those 2 hydrogens cannot be donated, or those 2 hydrogens cannot show its acidic character. Even in that case, actually it can be protonated, it can show its protonated form like H3Y minus or H4Y, because the hydrogens will not show its acidic character, so therefore it can be assigned as, or it can be assigned by the formula H3Y minus or H4Y. Whereas if you are going to make the pH higher and higher, so at a point of time all of its hydrogen may show the acidic character or may show the acidic nature. Therefore, if we just increase the pH, the stable forms of these EDTA could be either HY3 minus or Y4 minus, because at very high pH all of its hydrogens can show the acidic character. Moreover, at high pH the metal ions and also metal EDTA complexes may undergo hydrolysis to precipitate metal hydroxide. Thus the stability of this metal EDTA complex depends on the protonation of EDTA, metal ion hydrolysis, and complex formation of metal ions with ligands. So for each metal ion there is an optimum pH at which the formation of metal EDTA complex is maximum. So we have to keep in mind that these kind of titration where the metal EDTA formation is possible, there we have to maintain a optimum pH, because the stability of these kind of complexes are pH dependent, and these optimum pH is calculated from the hydrolysis constant of the metal ion and the stability constant of its complexes with the anion of the buffer solution. So here it is some kind of general consideration, and we have already covered these kind of things, that in this titration a complex compound is formed. Why a complex compound? Because there would be a metal ligand complex, there would be a metal ligand chelate complex, and it will be highly stable in nature. Why? Because it will form one kind of 1:1 complex in this kind of complexometric titration. In the next point, we have already mentioned that in this titration, the metal ions are estimated with the ligands. How the metal ions are going to be estimated with the ligands? See that the metal ions can form complex with these with these kind of ligands, with this kind of chelating ligands. It can also form complexes with the indicator also. But if the metal ligand complexes will be more stable, then in presence of that ligand, the metal indicator complex will be converted into a metal ligand complex. Now, how much ligands will be consumed at that time of the titration? From that data, we can back calculate the concentration of the metal ions. So, thus in this titration, the metal ions, or the concentration of the metal ions, or the quantity of the metal ions can be estimated. So that's the importance of this kind of complexometric titration. And now in the third point, the complex forming reagent used in complexometric titration is called complex ore. Complex forming reagent means that the titrant we are using, that the thing we are using to titrate the metal ions or the cations. So therefore it is the ligands actually. Example of this kind of complex ore could be EDTA, and we have already learned that EDTA is one of the most widely used complexometric reagent, or it can be called as one of the most widely used complex ores in complexometric titration. Here again I want to highlight how the metal ions are going to react with these EDTA ligands. Now I have already shown you that EDTA is mainly or generally represented or assigned as H4Y, or sometimes it is also represented as H4-EDTA. But see that EDTA is not generally used for analytical purpose. Why? Because it is very much less soluble in water. Whereas the sodium salt of EDTA, whichever I have just shown you in the slide, that is Na2H2Y.2H2O, this is the sodium salt of EDTA, and it is very much commercially available and appreciably soluble in water. But see, these cannot serve as the primary standard substance. Why? Because it can absorb moisture. It is generally hygroscopic. Now if it is absorbing moisture with itself, then its weight cannot be fixed, right? Or its weight cannot be constant. So therefore it cannot serve the purpose as a primary standard reagent. Then it would be a secondary standard reagent, right? Now it can be purified by heating at 80 degrees centigrade for 2 hours to get pure crystal of these sodium EDTA or sodium salt of EDTA. The better solution can be done by standardizing it with zinc acetate. Why? Because see, if it is not serving the purpose of being a primary standard reagent, then we have to, or we should standardize it with another reagent like zinc acetate. In that case, we will come to know about the actual concentration of these sodium disodium EDTA. Then we after that titration with that disodium EDTA with that metal ion, we can come to the conclusion about the actual quantity of the metal ions present in that solution. So now here I have again shown you some kind of reactions, that how the metal ions are reacting with these EDTA or the EDTA ions. Say for example, and in each and every case I have just taken H2Y minus 2Y because I have already told you that in aqueous solution it is stable as the it is behaving as dicarboxylic acid. So therefore I have written the form as H2Y 2 minus. So now whether the metal would be plus 2 charge, it would have the plus 3 charge or plus 4 charge, or the charge will be variable. Each and every time the complex will be of similar type with release of some kind of H plus ions. But here one thing you have to remember, that all these equilibrium are highly affected by the pH of the solution, right? Because they are just removing H plus ions. So all these equilibrium are highly affected by the pH of the solution. The lower the pH, lower will be the stability of metal EDTA complex. I have already told you that if you are just going to lower the pH, at that point of time it may not act as a dicarboxylic acid, alright, because at that point of time it can be protonated to be H3Y minus, or it may be stable as H4Y, because if you are just going to lower the pH, it may not act as the dicarboxylic acid. So if you are just going to decrease the pH value, then the stability of the metal EDTA complex will be decreased, because in that case the EDTA will be not stable as H2Y2 minus, it would show H3Y minus, or it may show H4Y. So it may not just give a good complex, or it may not give a stable complex with the corresponding metal ions. So the more stable the complex, the more lower is the pH at which the complex can exist, and hence the lower is the pH at which the titration with EDTA can be done. Here I wanted to show you some stability constant data of some kind of metal EDTA complex. See that in this case, when the charges of these metal ions are going to be increased, then the stability of these metal EDTA complex are also going to increase. But see, in case of these Ag plus, the metal EDTA complex stability constant is very small, that is 7.2, and that's why it cannot form that much of stable complex with EDTA. But other ions like magnesium, calcium, manganese, iron, aluminium, all these kind of metal ions are very much able to form 1:1 metal EDTA complexes, which are very stable in nature. Here one chart is shown that tells us how minimum pH is required for the titration with EDTA. That different kind of metal ions will bind with EDTA to form different kind of metal ion complexes, and the stability of these kind of metal ion complexes will be varied, right? So now we will discuss that what minimum pH a particular metal ion will titrate with EDTA. See, the first case is when the pH will be in between 1 to 3. In that case, zirconium, hafnium, thorium, iron with 3 oxidation state, and bismuth with 3 oxidation states can be titrated with EDTA. Now at pH 4.6, aluminium, iron, lead, nickel, zinc, manganese with +2 oxidation states, and finally copper, cobalt and cadmium can be titrated at this pH with EDTA. And then in the last part, barium 2+, calcium 2+, strontium 2+, and magnesium 2+ can be titrated with EDTA at bare minimum pH, which will be ranged in between 8 to 10. So that is the overall picture at the minimum, at what minimum pH different kind of metal ions can be titrated with EDTA. So thank you for watching this video. So in this class, we have already learned that what is mainly the complexometric titration, and in these kind of complexometric titration, how the metal ions and the complexing reagent is going to behave, and when we are just considering this kind of complexing reagent, why the EDTA is being considered as one of the most suitable one in that case, and how these EDTA will make these metal EDTA complexes with different kind of metal ions, and how they will be stable, how the stability will be varied by varying the pH. So this is for today's class. So once again, thank you for watching this video, and if you have any doubt regarding this class, you can directly contact us through the website www.nsinsti.com, or you can directly send a mail at nsinsti@gmail.com, or you can call, message, or WhatsApp us in the given number. Once again, thank you very much. See you in the next class.